What I want to do today is to finish up 7. And I've been taking my time with 7 so that we get this stuff worked out, because 8 then sort of snowballs, it gets worse and worse. And in 7 we are talking about really the first complicated mechanisms that you had to think about. Acid-base chemistry, we could talk about mechanistically, we talked about pKa, we talked about equilibrium, all that stuff, we talked about where the equilibrium would be. And now we've extrapolated those ideas into more complicated stuff like rate determining steps, how many steps on the profile, and putting these things together. It's not easy at all. You need to put some time into this. So what I want to start with today is a little bit of what I talked about on Friday, which is how do you decide whether it's SN1 or SN2? By the time we get to Friday's exam, you'll have done acid-base chemistry, SN1, SN2, and the E2, right? In the next chapter, I'm going to get through the E2 as well. So you'll have 4 different systems to worry about. Some of them are quite similar, they're closely related, but you're going to have to make decisions about what's going to happen based on what you know. How do you know what's going to happen in terms of an SN1 or an SN2? Well, some of these things are fairly obvious. We dealt with this on Friday. We said that if you have a simple system which is unhindered, methyl or primary, then you're definitely going to do an SN2. You can't do an SN1 because you can't get a good carbocation. Carbocations need branches to help with hyperconjugation. If you don't have those branches, you're not going to get a carbocation. So we can say sort of fairly concretely that simple primary systems will do SN2, and then simple tertiary systems will always do SN1. And you should have recognized by now the relationship, the converse relationship. If they can't do SN1, they'll do SN2. If they can't do SN2, they'll do SN1. And the problem is in the middle when you have the secondary systems. And so yes, the secondary systems can do either. And what we'll try and do today is to put some conditions in to show you why and how, and to be able to make those decisions. So the ones that will definitely cause you problems will be these guys, because they look like they're primary, but they're special. The one thing that trumps or beats hyperconjugation is resonance. If you can delocalize a charge, it's better than, say, an inductive effect, and it's better than hyperconjugation. So in both of these examples, you can actually take off the leaving group, and you can draw carbocations that are quite well delocalized. And so these things can give SN1, even though they look like primary systems, and especially with secondary systems. Now, the problem you're going to have to think about is what's the nucleophile? What are the conditions? And something I'm very big on for the 2 semesters is having you understand what's happening in that mixture in terms of pH. Not pKa, but pH. Is this reaction mixture basic? Is it neutral? Or is it acidic? Because if you understand that sort of very simple idea, you can start to make some fairly good decisions about what will happen for organic chemistry. So be careful. There are some generalities in terms of primary doing SN2 and tertiaries doing SN1, but then you get into the secondaries and they're a bit of a problem. A lot of this is driven by the nucleophile. Yes, you've got to worry about the substrate, and you've got to worry about whether it's crowded or not, whether it can actually support a carbocation or not, but you've also got to worry about the nucleophile. Is the nucleophile aggressive? Is it in a hurry to react? And those nucleophiles will be said to be strong nucleophiles. They're not that stable, they want to become something else. The obvious ones that we've dealt with, things like hydroxide. Hydroxide is reactive. And if you have a circumstance where it can't behave as a base, it might behave as a nucleophile. It will switch roles. And we recognize from early on that bases are nucleophiles and vice versa. So these guys here, you should recognize already as being strong nucleophiles. They will not sit around and wait for other things to happen. And by those other things, I mean carbocations being formed. These strong, powerful nucleophiles tend to attack a substrate and get the reaction finished. Other things that maybe you're not so common with, not so familiar with, any nucleophile here with a negative charge, the ones on this chart, are going to be strong. They are small for the most part. The larger ones, you can share the charge quite easily, and we can have sort of nice attack on a primary or secondary substrate. Now, weak nucleophiles. Why do you think F- is so weak compared to the other halogens? It's not because it's small, but because of what? If it was small, it should be a decent nucleophile, because then it can access places. What's the difference? Why is F- a weak nucleophile? It's highly electronegative. It does not want to share its electrons with anything else. Again, the first 4 weeks of class, everything just adds up. We're just putting it all together now. Why, for example, would hydroxide be a strong nucleophile and water be a weak nucleophile? Hydroxide is way more reactive. It's unstable. It wants to become something else, and that's why it attacks a molecule, whether it be in an SN2 or possibly in the next chapter, an E2. So this chart is your friend. You should have a look at it and decide that you're comfortable with it. The anions will typically do good SN2 reactions, and then neutral species will typically do SN1 reactions, because the neutral species are not in a hurry to do anything else. They're not in a hurry to attack, and they might also help out the formation of a carbocation. So over here, you'd have to say that these guys over here are good at SN2, and over here, they probably allow for SN1. So some sort of criteria you can use to understand this stuff. The third possible idea now is the leaving group. If you have a good leaving group, you can do an SN1, because that's the first step. That's the rate determining step. If you have a poor leaving group, maybe the SN1 isn't so good. So in this example, we're saying now that the leaving group is something that's capable and happy of taking off a negative charge. I minus, Br minus, the sulfonate that we saw on Friday, things that can delocalize that negative charge when it forms. So that leaving group now is going to be important in terms of making that decision. Can it break off on its own? Can we help it break off? And that will give us maybe an SN1. So the statement at the bottom I think should be fairly obvious. Weak bases make good leaving groups because they can stabilize, right? Strong bases are not stable. Why would they break off if they were not stable? So this idea that weak bases make good leaving groups I think is fairly general. And we looked at this chart to relate this to pKa's. Okay, the stronger the acid, the weaker the conjugate base, right? So whatever you recognize as a strong acid, its conjugate base is going to be a good leaving group. HBr, Br minus, good leaving group. HI, I minus, good leaving group. And then the one we talked about briefly was the sulfonate ester. This is a synthetic derivative. These are not found in nature. These are compounds that we've put together to help with these problems. And again, the context, you've built something over here which is very expensive, attached to this molecule. You don't want to destroy it. If you took what we've done so far, for example, add HBr, add HI, there's a good chance that those reagents will react over here and destroy what you've just made. So organic chemists have had to develop these other reagents to avoid that. What you can do here, instead of using HBr for this alcohol to do a substitution process, you can put one of these things on, a tosylate, a mesylate, or a triflate. And the process is the same. You start out with a chloride. So to make a mesylate, you'd simply have a chloride here. To make a triflate, you'd have a chloride there. And you swap out that chloride on the sulfur, and that gives you this sulfonate ester leaving group, right? So a sulfonate anion as a leaving group is very good. That's one step, and it avoids the use of acid. In fact, we'll see, and we may already have seen, the fact that pyridine is weakly basic. So this is not acidic at all. So whatever you put over here is not going to suffer. It's not going to react with an acid because there isn't an acid there. You've made this a good leaving group. Now, this is maybe the first example we have seen of a full SN2 reaction, where everything's in there. First of all, you make a good leaving group, and then you look at the conditions. You're looking for sort of triggers for Friday. You're looking for things that you recognize to be able to help you work out the problem. This is a good nucleophile. It is N3 minus. It's small. It can get places, right? The fact that it's negative is going to make it fairly reactive. And we haven't talked about this yet, but DMF is a solvent. And that solvent is a compromise that allows you to dissolve a salt up with a non-polar organic material. And that's what we really have to finish off in this chapter to get it done. So now we have all the conditions. This just screams at you SN2. Hopefully by Friday you'll recognize that. And so we have the nucleophile come in, and it has to attack from the back, and then it boots out the sulfonate. And the reason this is such a good leaving group is because when you put the negative charge on the oxygen, you can delocalize. Yeah? The more delocalization you've got, the better. So those are very, very useful groups. By now you can talk about halides coming off. You know how to make halides from alcohols and HBr. And now we can talk about sulfonates. We have a group of leaving groups that we could use to do this sort of chemistry. Right. Solvents are something that you will have to spend time thinking about, not only in my class, but in biochemistry. In biochemistry, you're kind of limited that the solvent is water. So you have to think about how organic molecules are going to interact with water. You already know from your own experience, some of them don't dissolve in water, some of them do. That's biochem. In this class, we have developed solvents that will allow for these things to dissolve up. Again, it's a swimming pool idea. You need to have some water in there to be able to swim around, or the molecules can't find each other. So we talk now about, quickly, this idea of SN2. This is a relative rate of reaction for an SN2 process. It doesn't say it on the slide, I don't think, but this is for SN2. If you put side by side 5 flasks, and you did the same reaction in 5 different solvents, you measured how fast they went to completion, you'd find that they're quite different. You'd find that the use of something like methanol is very, very, very slow. The use of something like water is a little bit faster, but not by much. But then you get into some of these synthetic solvents that we use. DMSO, I'll show you the structure in a second, very, very fast. Something about DMSO is allowing this reaction to go a lot faster. DMF, you will know them by the acronyms, you'll also know them by hopefully the structures. DMF allows this to go much faster, okay? And then thinking about things like acetonitrile, 5,000 times faster, simply by swapping the methanol that we started with, which is not too different in structure, for this CN group. Now the engineers have to worry about this stuff. You're going to work in a plant where you have to scale things up. A lot of you go into process engineering, for example. Process engineering is where the chemists meet the engineers, and the chemists have done things in a small flask. Maybe they've made a kilogram or something, and the process engineers have to turn it into 100 kilograms for whatever, for clinical testing of a drug, for example. And these solvents are important, and there are also limitations. In my lab, I can use some of these dangerous solvents on small scale, no problem. But if the engineer has to build a plant to make this on a ton scale, there are some solvents you can't use. So this is really important stuff in the beginning of it. Those rates, don't memorize them. You will know that the molecules on the left are slow in the SN2, and the molecules on the right are fast. And there's a fairly obvious, fairly simple reason. What can these two solvents do that these solvents, which don't contain OH groups, cannot do? Hydrogen bond, absolutely, they cannot hydrogen bond. And so hydrogen bonding now will have some role to play in how fast the SN2 reaction goes. As you're designing experiments, you have to be very careful. You have a cupboard full of solvents, and you have to choose the right one, or else it doesn't go fast enough, doesn't go quickly as it could. Ashley? That's going to work out in a minute, yes. Yes. So there is going to be a converse relationship here. So the molecules on the left don't allow the SN2 to go very fast. The molecules on the right do. And basically we have a definition we need to pick up here. On the left, yes, they're very polar. And why do we need polar material here? Because we have a salt, which is polar, and possibly the organic molecule is polar. But there has to be some compromise. You think about the limitations of water with organic solvents or organic materials. A lot of them don't dissolve in water. So solvents, often you can't use water as a solvent. But on the left, the issue here is the polar protic. Protic means it's got a proton that's acidic, and therefore it's going to hydrogen bond to a nucleophile. So the definition now, any molecule that has an acidic proton of an appreciable pKa. And what I mean by that is 16 and lower. Alcohols and lower are going to be called polar protic solvents, and they slow down the SN2 for a reason I'll show you in a second. On the right, we have solvents called polar aprotic. So aprotic meaning they don't have. Think about chiral, achiral, protic, aprotic. Okay? They don't have a proton that is acidic, and therefore they're not going to interfere with a nucleophile like the polar protics do. So we have a basic definition, and then we have to worry about what that definition is trying to tell you. Polar protic, not so good for SN2. Polar aprotic, very good for SN2. Now, I don't know if you can see this too well, but there's the basic idea. At the bottom left, you can see the protons, and you know from your pKa ideas that these things are protic. Okay? This is not as acidic as the others, but it can be considered polar protic. We don't use ammonia very much. We do in one or two reactions. We certainly use ethanol a lot, and methanol and water and acetic acid. They are all acidic to a degree, and therefore polar protic. And for a reason I'll show you in a second, they slow down the SN2. On the right-hand side, I have, and I hope if you've got these slides in front of you, you can see this, dimethyl sulfoxide. This stuff has been used for years and years for people who had arthritis. You used to be able to buy it at the drugstore and then take it home and you put it on your knuckles, and it was supposed to alleviate the symptoms of arthritis. Unfortunately, it's not very good for you, and you can't do that anymore. But it's a really, really, really good organic solvent. It's the only organic solvent I know that I can taste from about 10 yards away. It's absolutely disgusting stuff, so be careful with it. It does not have an acidic proton, so we don't have to worry about hydrogen bonding. Acetonitrile. Acetonitrile is this one. Okay, CH3CN. It has a triple bond between C and N. So if you put delta plus and delta minus in there, you'll recognize very quickly that it is going to be polar. But there's nothing in there that's particularly acidic, and so it doesn't hydrogen bond. DMSO over here is this one. Okay, this is pretty good. We avoid it if we can in the lab. The biochemists use it a lot because it's very soluble in water and it allows for dissolution of their reagents. But in the organic lab, we try to avoid that stuff because it's nasty. Our favorite is this one, DMF, dimethylformamide. There's the name down there, dimethylformamide. This is not an acidic proton. We'll see that in the second semester. That is not acidic at all. So this molecule is not a hydrogen bond donor. And DMF is a compromise. It's a good polar aprotic because you dissolve lots of stuff up in here. Some salts will dissolve in DMF, even though it's an organic solvent, and the organic reagents will dissolve up. So you get an homogeneous mixture that allows you to swim around and find each of the molecules. The problem with DMF is then it boils at about 160 degrees. And if it boils at 160 degrees, you have lots of sort of latitude for raising your temperature, but what about when you want to get rid of it? How do you get rid of liquids? How do you purify liquids so far? Distillation, right? Evaporate them through distillation. So if you're boiling at 160 degrees and you're going down to nothing, a residue in your flask, you're now heating your molecule. But what you want to get back out of that mixture, you're heating it at 160 degrees. And sometimes that's a problem. So we play tricks in the lab. You'll see some of those later where we reduce the pressure. We do these evaporations at high vacuum so it doesn't boil quite as high. But DMF now is probably the best of the lot as far as I'm concerned because it does boil quite high and you can play with the temperature, and that gives you very, very good SN2 reactions. Why? It doesn't hydrogen bond. The ones on the left do, the ones on the right don't. So why on earth should that make a difference? Why should hydrogen bonding make a difference to an SN2? What's the actual idea behind that? Well, number one, you are trying to dissolve things up. If you can't dissolve things up, typically at this level, the reactions don't work. So that's one thing you need to worry about. Get stuff dissolved up in a solvent that isn't too dangerous and a solvent that you can remove when you need to. So you could think about water. Well, water, it's everywhere and it's cheap. So why not just use it? And the problem is, it is very good at dissolving things up, but it's a bit too good because the hydrogen bonding is going to surround the nucleophile. Let's say you dissolve NaClO. in a reaction. You want to use Cl- as your nucleophile. Well, fine, it dissolves up, but then you get this. You get extensive hydrogen bonding between the delta plus H's on the water and the chloride ion. And that's a big problem for the SN2. What do you think that does to the chloride? Stabilize it or destabilize it? Stabilizes it. You don't want your nucleophile stabilized. That's one obvious thing. What else? It's almost as if you've put your chloride inside a bucket of water. It's surrounded now by water molecules. And what's the rate determining step in an SN2? The nucleophile attacking the electrophile. Well, all of a sudden, this nucleophile is surrounded by water molecules getting in the way, slowing down the approach to the carbon, the electrophile. So it slows it down because it's hydrogen bonding, and therefore it's not very good for a polar protic system to be used in the SN2. It gets in the way. It stabilizes the nucleophile, which we don't want, and it gets in the way physically. So what about a polar aprotic? Well, polar aprotics, such as DMSO on the right, they are able to stabilize the plus charge. Whatever the cation happens to be, in this case the metal sodium plus, the O negative or delta negative ends of the sulfoxide can stabilize the Na plus. That's a good thing, because you want to get this stuff into solution. But is it stabilizing over here? No, there's nothing there. Now, two reasons. It's the opposite now. That thing is reactive. It's not being stabilized. It has to go into solution because the sodium went into solution, and this is an ionic pair that has to have to go together. And so the Cl- now has been dragged into the solution, so that's good. And it's also not stabilized. And there's nothing surrounding it, getting in its way. So this now is the whole basis of why this is good. And to show you that sort of from another book that I brought this picture, there you go. That's why the SN2 is slow in the polar protics. You can see all of this hydrogen bonding now with the Cl-. Basically, there's a whole sort of bunch of stuff getting in the way of the nucleophile. That's not what you want for the SN2. So just a few more slides now to finish this off, and then we'll get into 8. These two pictures are side by side, trying to show you what happens for an SN1, what happens for an SN2, to answer Ashley's question from before. For an SN1, you've got to worry about what gets formed, and you've got to worry about what the effect of the solvent is on that material. Is it going to help that stuff get formed or not? On the right, for the SN2, is your solvent going to slow the reaction down by binding or hydrogen bonding to a nucleophile and getting in the way? And then you have to decide what solvent you want to use. So I'll start on the right because that's what we just did for the SN2. Polar aprotic solvents are very good for this because they don't stabilize the nucleophile. Right? You're starting up here because the nucleophile is quite reactive. That means a lower activation barrier. That means a faster reaction. Down here, if you use a polar protic solvent, you've got problems because that polar protic solvent will stabilize that nucleophile and also get in its way physically. So can you see the difference there? Polar protic, much higher activation barrier because things are being stabilized. You're starting at a lower point. So you want over here your polar aprotics, you want your DMF, your DMSO, your acetonitrile. On the left-hand side, we've got the opposite now. We've got the SN1. What gets formed in an SN1? What's the rate determining step in an SN1? Loss of the leaving group, right? The formation of what? Carbocation. So are we okay with the fact that a carbocation is a charged species? Yes? It's a charged species that's missing out on some electron density. So we need some help. And quite often in the SN1 reactions that you will find that you have to worry about, the solvent actually becomes a nucleophile. So what do I have on, for example, H2O or methanol, the OH group? What do I have on there that will stabilize a positive charge? Say again? Ooh. Other side. A pair of electrons, right? Those pairs of electrons will help stabilize that. So in the SN1 process, we'll find that this allows for the leaving group to break off by hydrogen bonding, and it also will then stabilize the carbocation. So the polar protics are good here, and the polar aprotics are not so good. So it's kind of the opposite reasons. If you understand the difference, one has a hydroxyl, one doesn't, that's really all there is to it. Everybody all right? Good weekend? Weekend? What's a weekend? Go on, Joe. No, be careful. The water does not react. It does not break apart itself. The water is facilitating the leaving group breaking off. Okay? This is what this slide is about now. That's what this slide is about now. So to summarize, polar protic, good for SN1. Polar aprotic, good for SN2. Wake up! It's only bloody Monday, for crying out loud. Fall asleep on Friday. Polar protics, good for SN1. Polar aprotics, good for SN2. With that in mind, why? So here you've got some pictures showing what the solvent does. And this is the whole idea of facilitating the loss of a leaving group. Okay, there's some substrate. It's tertiary, let's say. And we want to think about why this can break off spontaneously. If this thing wants to start breaking off, it needs some help. X is not just going to drop off. It wants to be dragged off. So what we'll have, the idea, or what we'll see here, is the idea of whatever this solvent happens to be, the red, whatever they are, lozenges, happen to be the solvent. And if they have something that allows for binding to that X as it's becoming delta negative, it will stabilize that system and it will lower its energy. It will make the reaction faster. So this is going to be your polar solvent, right? Polar protic even better for the SN1 because this is good. Over here we've got the possibility now of the opposite. Maybe we can also help stabilize the carbocation. And so again, it's sort of evidence for SN1. Polar protic is good because they can help stabilize what's happening. SN2, polar protic is bad because they help stabilize what's happening. You don't want that in the SN1, in the SN2. That probably didn't mean anything. That's recitation this week. That's office hours this week. Have a look at it. Be happy with what you're looking for. Again, you're looking for clues. When I finish off here with a few examples, I'll show you some clues as to what to look for SN1 and SN2. Overall, to summarize all that, because Chapter 7 is the beginning of the big idea of mechanism for chemistry and biochemistry, if your substrate happens to be methyl or primary, you're doing an SN2 reaction because it cannot do an SN1 reaction. The carbocation would be awful. You need strong nucleophiles. You're going to recognize as you practice, because you're going to practice a lot, a good nucleophile is not going to wait around for a carbocation to get formed. It's going to go in, do its business, and it's done. It's going to form a bond and then kick out the leaving group. The type of leaving group needs to be good, okay, to facilitate a fast reaction in the SN2, and you want a polar aprotic solvent so that you don't slow things down. You don't stabilize things necessarily. For the SN1, typically it's tertiary and some of the better secondary systems. You're looking for a weak nucleophile. Go back to that table and look at what weak nucleophiles were. Things like water, things like methanol, they allow things to happen. They allow for a carbocation to get formed. And then you also need a good leaving group for this, because it has to break off in the rate determining step. And now you prefer a polar protic solvent because the hydrogen bonding within that solvent allows for stabilization of the leaving group and of the carbocation. Now again, you can memorize some of this stuff, but hopefully it starts to sink in and we start to understand things, because within the next month or so, we'll be using this to build our own systems. This chart is just to summarize. We've done all of those reagents. We've seen those at least in class, I would think, and certainly in recitation. How do I know this is going to be nucleophilic? Well, it's a salt, O-. Same reason it was basic. Over here, Cn-, right? Over here, S-. Here, O-, O-, X-. So those are all nucleophilic, and they're all going to attack some substrate which has a leaving group attached. And the whole point of this slide is, without realizing it, you've now got access to all of these functional groups, simply by doing substitution chemistry from that chapter. How do you pick all that stuff up? Well, you put your phone down at the back and take your headphones out, and you listen or you fail. It's as simple as that. How many times do I have to tell you, John? Obviously too many. Well, these are ways of making functional groups. Do you memorize that chart? Okay. Or do you understand that it's all we've done so far is substitution? Nucleophiles, electrophiles, leaving groups, that's all you have to do. Examples. Finish off and move into chapter 8. How do I know this is going to be SN1? Tertiary starting material. It's a tertiary starting material. You have a weak nucleophile. How do I know it's a weak nucleophile? It's neutral. It is neutral. It is also polar protic. They are good conditions for an SN1 reaction. Why not SN2? Too hindered. Why not SN2? Polar protic stabilizes the nucleophile. That's no good. So that is going to tell you it's a polar, an SN1 reaction. And I look at the starter material. What's special about the starter material? What do I have to worry about in the starter material? It's chiral, right? It's a chiral starter material. So what do I expect for the products? Say again? It's going to be racemic. Very good. You're going to get racemic mixture, right? You will find out very quickly on Friday where you stand in this class. The average is usually in the 60s, but the low score is usually about 7. Because people haven't put the time in or they're too busy messing with their damn phones. This is a racemic mixture. What's the alpha D for a racemic mixture? 0. Why? They cancel out. Now, looking at this one. What clues are there in that question that hopefully helps you focus on the fact that it's going to be an SN2 process? DMF is one, yes. DMF is something to focus on. It's a good polar A protic solvent. And what about CN-? It's a negative nucleophile. It's one of our class of very good nucleophiles. It's small, it's easy to get to. So we can use that as an SN2 reaction. So it's a secondary substrate. Everything's set up here for an SN2 because of the criteria we've just developed. What's the answer in terms of the product? What stereochemically is going to be different? What's the word we use? Inversion. Good. Some people are on top of this stuff. Inversion. If alpha D for the starter material is plus 12, can you tell me alpha D for the product? Why not? It's a different molecule. It's not related at all. Down at the bottom. Now this is a primary substrate, and it's also benzylic. So this is where it gets a bit tricky. And it's really tricky if you're asleep. Good Lord. We've got a nucleophile. It's a powerful nucleophile, and it's a good polar aprotic solvent. So that tells me SN2, not SN1. So I'm going to attack, I'm going to kick this out. Do I need to worry about stereochemistry in this one? Why not? It's not chiral, it's achiral. And that's that. Would anybody like to say anything about chapter 7 apart from goodbye? Would anybody like to say anything? Did the Browns win? Did the Browns play? Was there an NFL schedule this weekend? What happened? They won. Wow. I don't really care, but you know. So let's think about chapter 8, because this is now moving into more interesting stuff. Chapter 7 homework is up there. Chapter 7 quiz is up there. The quiz is due the Sunday after the exam, so you get no rest on this stuff. Welcome to 3000 and above. And we're going to get into 8 because 8 takes me a while. I have 103 slides for 8. I have many more for 9. I have a lot for 10. I have more for 11, and I have a lot for 12. So we're getting into it now. We're getting into the real sort of where study discipline and maturity becomes a real issue. Chapter 8 is all about alkenes. We've gone away from sp3. We're going to move into sp2. And this is where it's up to you to be on top of things. Use the resources we've got on the website. Use Tyler, use myself, whatever you need to keep this stuff straight. We can see now that the shapes of the molecules ought to change because we went from sp3 to sp2. We'll find in this chapter that we don't do substitution reactions. We do something called elimination. We'll show you how to make an alkene, how to name these alkenes, and then where they're useful. Examples of these things. At the top, arachidonic acid. For those of you who make it to biochemistry, you'll learn about arachidonic acid. It's a precursor to all sorts of things like prostaglandins, right? Modulators in biochemistry. And we have these double bonds. So now we have a different hybridization pattern. This is sp2. So around that double bond, what shape do you expect? Flat. It's going to be flat. And this is one class of alkene that we'll see a bit later on that is said to be separated because the double bonds have an sp3 carbon in the middle. And arachidonic acid has several functional groups, which you ought to recognize by now. And you ought to be able to tell me its pKa. What's its lowest pKa? 5. Good. We have down over here my favorite compound since I came to North America. This is vinyl chloride. And the most popular use of vinyl chloride is in the synthesis of polyvinyl chloride, which is vinyl siding on your house. Now, do you think vinyl chloride and polyvinyl chloride dissolve in water? You would hope not, or your house would dissolve. That would be a silly thing. It's very non-polar, and so it's not going to allow water through. That's the whole idea of that stuff. So next time you look at the vinyl siding, you now know what it looks like. It's a chloride. And it's an alkene precursor. We'll make the polymer later, and we'll do polymerization a lot later, and we'll talk about the properties there. Now, this type of alkene over here, vitamin A, is said to be a conjugated alkene. That will become a bit later. But you now have alkenes which are all next to each other. There's no separation between these things. That will make a difference in terms of electronic communication. When we get there, it makes a difference in things like the fission process. These molecules become really interesting. So alkenes, you need a double bond. And of course, you need a way to name them in a minute. So I've got today and some of Wednesday to get this finished, or get this into it. This is a problem for everybody who gets into this class now. Even the ones who are taking it seriously, even the ones who are studying. This becomes just hard work. Because I've just spent the best part of a week, maybe 4 lectures, telling you that if you treat an alkyl halide with a nucleophile, it will give you a substitution product. It will. That is the substitution product. There's my alkyl halide, there's my leaving group, there's my nucleophile, there's my substitution product. But where biology is perfect and typically gives you one outcome because of, however long in terms of evolution, organic chemistry in the lab isn't quite so much, isn't quite so straightforward. You get mixtures, you get byproducts that you don't want. You get major and minor isomers, and it can be pretty problematic in terms of actually separating them. So hydroxide is a good nucleophile, absolutely. But where did we first meet hydroxide? What was it? It's a base, right? It's a base. And the whole point now is that any nucleophile, Nu minus, is also a base. They are really the same. So we get into complications now because we can have reagents that have two roles. Depending upon what it's attacking, depending upon the substrate, we'll get some substitution and we'll get some elimination, or we'll get mostly elimination and a little bit of substitution. We'll get mixing up of the mechanisms. That's where things start to become more interesting, but also more challenging. So an elimination process now is going to happen in which a molecule, in this example of HBr, is going to get taken out of that molecule. It's going to get eliminated. You take something out, you eliminate it. So we're not substituting here. We are eliminating by taking out this proton at the beta position specifically. It doesn't work down here, and it doesn't work down there. It has to be next door. And you put a double bond in between the two carbons that had those two pieces. So that's going to give me an alkene. That alkene is flat. It's changed shape around that part of the molecule, and it has interesting properties, which is chapter 9, addition type of chemistry. So the basic definition is now different. Substitution, you replace something. Elimination, you're going to rip something out. Examples from nature, why you have to worry about these things, even the engineers. All sorts of bacteria will use these things for biosynthesis. People start to bioengineer bacteria to do all kinds of wonderful things. So these are engineering type ideas. Limonene smells like oranges. This is an alkene with two double bonds in there. You'll learn today that that's one type and that's another type. And you have to categorize these like you did for primary, secondary, tertiary cations. They all have different groups. They're all part of different families that then do different chemistry sometimes. Cholesterol, we've seen alpha-pinene. This smells like it's part of paint thinner, pine resin. You see the alkene there. It's got this marvelous bicyclic structure, quite complicated, but it's still a flat alkene around that carbon here. And this is cholesterol. Cholesterol is wonderful. I mean, it's got all those chiral centers. Imagine doing R and S for that on Friday. Yeah. That would be great, wouldn't it? You spend all your time doing that. Maybe. And you've got this alkene. So that alkene is now reactive. We have two major functional groups in here, the hydroxyl and the alkene. And very quickly here, we're building up complexity. We're building up how organic molecules talk to each other. Uses of these things, just to get it out of the way. Petroleum provides us with all kinds of different materials. Alkanes, alkenes, benzene derivatives. And you can see here two of the major, all right? Ethylene and propylene. We make polyethylene, we make polypropylene as plastics. And you can see now that ethylene can be turned into ethanol. Ethylene oxide becomes really important later, the dichlorides. We can make it into aldehydes and acetic acid. We can make it into vinyl chloride to make vinyl siding, things like that. We can turn it, what's ethylene glycol? Anybody? Antifreeze, we can use that too. And we've got all these possible derivatives from an alkene. This isn't so much of a concern right now, okay? But after the next exam, when I'm left with the people who can do this stuff and who want to do this stuff, chapter 9 is enormous. I won't even say it's big, it's enormous. Don't worry about that stuff until 9, but this is just showing you how alkenes are useful. They're very, very, very important starter materials to be able to do all the sorts of different things. So these are industrial processes. We make these things on the ton scale, and they're then fed back into the industry and fed back into labs to be able to do other chemistry. So alkenes are key. Well, we need a nomenclature system. Get this out of the way now, and we'll do some chemistry. Everything you learned about the naming system so far still applies. But let's think about this from a logical point of view. Can an alkene, sp2, can it be R or S? No, it cannot. It needs to be sp3 for that. But it can have an isomerism. We'll see that in a minute. You need to identify the parent compound, typically contained in the alkene. You need to identify the substituents. What else is branched off of that chain that hasn't been taken into account yet? You need to give some numbers so that the reader can tell what molecule we're talking about, its actual identity, and you need to arrange the substituents alphabetically. Those are things we've already done. But of course, we're getting better at this, and this is pretty straightforward. So On Friday, you might see questions that have an alkene and bromide and fluoride, and over here is R and S, and over here is different isomerism. That's where we need to be. So on the left, I have pentane as an alkane, no double bonds, no functional groups. On the right, I have pentene, and pentene is an alkene, so it gets a different ending. Pentene right there. Thinking about the rules, identify the parent compound. So in a simple system like this, you want to make sure that alkene is in the parent chain. So everything else becomes a substituent. What would you call this substituent? Let's call it Brian. What do you want to call it? Propyl, thank you. Propyl is more appropriate. So the parent here is heptene. Why? Because even though it's not the longest chain, it's got the alkene in it. It has the functional group in it. Adding things up, we want to make sure the numbers are as small as we possibly can. So the alkene now. Let me say this carefully. We're at the beginning of prioritizing our functional groups. We said previously that the alkyl groups and the halides have the same priority. They're as unimportant as each other, if you like. Right? They're at the bottom of the chain. When you put an alkene in here, it's got more chemistry, it's more interesting, it's going to have a higher priority. So the alkene now is key. And you can see on the left, I've got the alkene now numbered as low as possible. And over here, even though my alkyl groups are going to be at higher numbers, the alkene is more important, so it wins. As we get after we come back after this next exam and we talk about alcohols and stuff like that, it gets more difficult again. Jacob. Between 3 and 4, yes, because then you get the 3 as opposed to the 4. Yeah, just keep it small. Yeah. Okay, now, again, this is, I don't know the history completely behind this, but I think it's a European, North American thing, where I think in North America you say this, and in Europe you say that. It's like tomato and tomato, right? It's the same thing. You say everything wrong. This idea of putting the number in to tell the reader where the alkene is. So in this example, the 2 is telling you that the heptene, the ene, is at carbon 2. This is exactly the same thing. It just seems to be some sort of idea that's just it's been maintained over the years. The 2 is also telling you where the alkene is in the starter material. It's exactly the same thing. So if you read those, they're the same thing. Don't worry about that too much. But again, you need that number, or else you'll get isomers. Common ones that you'll have to worry about, especially the engineers. Ethylene. If you're a chemical engineer and you don't know what ethylene is, you shouldn't be a chemical engineer. Okay? Ethylene, feedstock material for the industry. Propylene. These are fairly obvious, right? F, 2 carbons, ene at the end. Prop, 3 carbons, ene at the end, propylene. And then the one that you'll see a bit more of later, styrene. What does styrene give you? Polystyrene, styrofoam, right? Which is a massive, massive problem these days because we can't get rid of it. So keep an eye on those things, and then, unfortunately, you have to know these names. You have to know these substituents. Vinyl is the smallest unit of an alkene when it's substituted as something else. So you might have vinyl cyclohexane, something like that. It's a substituent on something else. Allyl, we've already seen when we did resonance. Allyl is a 3-carbon piece in which a double bond is next to a carbon like that. Phenyl, I think we've seen already. Okay, not phenol, but phenyl. Bit different now, just a benzene ring attached to something else. And methylene is a CH2 group at the end like that. Those are very common substituents in pharmaceuticals, in organic chemicals, in commercial products and stuff like that, so you need to be comfortable with them, what they look like. So they all contain alkenes. They're all going to do interesting stuff. This is probably the last thing I'll get to today, but that's good because then I can get about 20 slides done on Wednesday and be ready for the exam. You need to be able to count. Now in chemistry, you don't need to count much past 4. So if you can get to 4, we should be okay. You're going to classify alkenes based on their substitution patterns like you did for carbocations, like you did for tertiary and secondary alkyl halides. And this, after the exam, leads into all of the background as to why you get one compound more than others when you have a choice. We'll leave that till after the test. I've got a monosubstituted alkene. Why is it monosubstituted? Well, the 2 carbons of the alkene have 1 other carbon attached. Take a minute to learn that, and it happens, it's the same every time. So this is a monosubstituted alkene. If you're not happy with that, as you practice, put the hydrogens in. If it's got 3 hydrogens, it's only got 1 carbon attached, and therefore it's monosubstituted. So I am not counting the alkene carbons. I'm counting away from the alkene carbons. I've got disubstituted here, where I've got carbon and carbon, which I don't count, have 1, 2 different groups attached. That's said to be disubstituted. You'll see here that, again, it's useful sometimes to put the hydrogens back in. If you do that, you can see that that thing only has 2 carbons attached. Not 3, not 4, not 5. 5 is just impossible. Don't be doing 5. This one over here, 3, try. What's the problem with this guy down here? It only has 2, right? That's not a trisubstituted. This one is. Tetrasubstituted is this. And we'll see after the exam that the more substituents you get, the better. The more stable the product happens to be. Well, that leads to also a little problem here. The idea of these guys. Maybe I'll get to that today, if not Wednesday. So with that idea in mind, I'm telling you that the more groups you have on the alkene, the better. We can start to worry about how alkenes are formed. Alkenes are fundamentally different to alkanes. In an alkane, you can rotate around every bond. All you have are single bonds, and single bonds are always rotating. Marissa, you okay? You still with us? Over here, focus. Yeah? Okay. They're always rotating quickly. Always rotating. You can't stop that. Well, the problem with a pi bond is, if you rotate around it, you break it. That's not going to happen. So pi bonds, under normal lab conditions, are not going to rotate. Simply because you have a pi bond, which is set up above and below the axis of the single bond. And if you think about how to rotate that, you'll break the pi bond. If it goes to 90 degrees, it's broken. That takes a lot of energy, and that's not going to happen. So be very careful. That rigidity, this is trying to make sense here, this rigidity now is very similar to the cycloalkanes. When you had alkanes on their own, everything rotated freely. And then you tied things together to make a cycle. Is that entropically favored or disfavored? Disfavored, right? You've taken away some of its freedom. Yeah? Now, this alkene does the same thing. And in cycles, if I had groups on the same side, what was that called? Cis. And if I put them on the opposite side, what was that called? Trans. Now look at this with the alkenes. I'm going to get molecules that are very similar in their relationship. Because the alkene is trapped and it cannot rotate around it, we're going to get something called a cis alkene and something called a trans alkene. The cis one is fairly obvious. I'll just finish off with this now and get to recitation. But what you need to do here is to think of this like an axis, or whatever you want to call it, a river, going through the 2 carbons of the alkene. And then you ask the question, where are my most important groups going to be? We're going to use the Carnegie-Prelog rules again, like we did in RNS, but I'm going to tell you that this carbon and this carbon will beat this hydrogen and this hydrogen for the same reasons as they did in the RNS material previously. So they're on the same side of my axis, therefore this is the cis alkene. On the right, if I draw that axis again through the alkene, carbon here and carbon here are on the opposite side of that. We'll call it a trans alkene. So on Wednesday, I'm going to get through. I'm going to tell you where I'm going to get through. If this thing will let me. There we go. My plan on Wednesday, for those of you who are keeping up and are staying awake, is to get through some evidence for what's called the E2 reaction. Right? So I will get through to section 8.7, and that's what you'll get tested on. Bye.